Fresnel diffraction. Early treatments of this phenomenon. Some of the earliest work on what would become known as Fresnel diffraction was carried out by Francesco Maria Grimaldi in Italy in the 17th century. In his monograph entitled Light, Richard C. Mack, Lauren explains Fresnel diffraction by asking what happens when light propagates, and how that process is affected when a barrier with a slit or hole in it is interposed in the beam produced by a distant source of light. He uses the principle of Huygens to investigate, in classical terms, what transpires. The wave front that proceeds from the slit and onto a detection screen some distance away very closely approximates a wave front originating across the area of the gap without regard to any minute interactions with the actuum. The result is that if the gap is very narrow, only diffraction patterns with bright centers can occur. If the gap is made progressively wider, then diffraction patterns with dark centers will alternate with diffraction patterns with bright centers. As the gap becomes larger, the differentials between dark and light bands decrease until a diffraction effect can no longer be detected. Lauren does not mention the possibility that the center of the series of diffraction rings produced when light is shone through a small hole may be black, but he does point to the inverse situation, wherein the shadow produced by a small circular object can paradoxically have a bright center. p. 219. In his Optics, Francis Weston Sears offers a mathematical approximation suggested by Fresnel that predicts the main features of diffraction patterns and uses only simple mathematics. By considering the perpendicular distance from the hole in a barrier screen to a nearby detection screen along with the wavelength of the incident light, it is possible to compute a number of regions called half-period elements or Fresnel zones. The inner zone is a circle, and each succeeding zone will be a concentric annular ring. If the diameter of the circular hole in the screen is sufficient to expose the first or central Fresnel zone, the amplitude of light at the center of the detection screen will be double what it would be if the detection screen were not obstructed. If the diameter of the circular hole in the screen is sufficient to expose two Fresnel zones, then the amplitude at the center is almost zero. That means that a Fresnel diffraction pattern can have a dark center. These patterns can be seen and measured, and correspond well to the values calculated for them. The Fresnel diffraction integral. The Fresnel approximation. Fresnel diffraction. Alternative forms. Convolution. Fourier transform. Linear canonical transformation. From the point of view of the linear canonical transformation, Fresnel diffraction can be seen as a shear in the time-frequency domain, corresponding to how the Fourier transform is a rotation in the time-frequency domain.